In this lesson, we're going to cover the chain rule. Now, the chain rule is another differentiation rule that expands the types of functions that we can differentiate. And to see that, consider these two functions. F of x equals the sine of x, and g of x equals x squared plus x plus 1. Now, we know how to differentiate both of these functions right now. We can do that. And we can also evaluate the derivative of the sum of those two functions. That would just be by using the sum rule. We can also evaluate the derivative of the product of those two functions using the product rule. And we can even evaluate the derivative of the quotient of those two functions using the quotient rule. However, we do not have any rule right now that tells us how we can evaluate the derivative of the composition, f of g of x, which in this case would be the sine of x squared plus x plus 1. We don't have any rule that we can use to evaluate the derivative of this function. Well, that's exactly what the chain rule is going to address. And the way the chain rule works is it allows us to evaluate the derivative of the composition of two functions by relating the derivative of the composition to the derivatives of f of x and g of x individually. That's the way the chain rule works. All right, now let's take a look at this. Now, before we can use the chain rule, we have to become comfortable with being able to write functions as the composition of two functions which we know how to differentiate using the rules that we already have at our disposal. So let's take a look at this example. We have a listing here of some functions, and we want to write these as functions as the composition of two functions, two individual functions, which we do know how to differentiate. You see, right now, we don't have any rule for which we can evaluate the derivative of the square root of x cubed plus x squared plus 5x plus 1. We don't have any rule that allows us to evaluate the derivative of this, nor the derivative of this one, the cosine of x cubed plus x plus 1. Nor can we evaluate the derivative of this. But let's see if we can write these as the composition of two or more functions, and in which we know the derivative of each of those functions individually. Well, let's take a look at part A here. Well, notice that we can think of this, we see an inside piece here, x cubed plus x squared plus 5x plus 1, and then an outer function, which is the square root. So if we let f of x be the square root of x, and g of x equal, then we see that this function y of x is actually then the composition. It's simply f of g of x. And each of these functions we know how to differentiate. So there we've written y as the composition of two functions, each of which individually we do know how to differentiate. Let's look at this one. Well, we see an inner piece right here is the x cubed plus x plus 1, and then an outer function, which is our cosine x. So let's let f of x be the cosine of x, and g of x, that's going to be, and then we see that the function y is just the composition of those two functions. And keep in mind, we know how to differentiate cosine, and we know how to differentiate this polynomial, x cubed plus x plus 1. But we don't know right now how to differentiate this. That's what we'll get to. Now let's look at this one down here. Now this one's a little more complicated because it's going to involve the composition of three functions instead of two. So we see an inner part right here being the tangent of x squared plus 4x plus 5. So let's and we see the outer function being the cube root. So let's let f of x be the cube root of x, or x to the 1/3. And then we're going to let g of x, well, that's going to be the tangent, but we're going to write it as the tangent. We're not going to say the tangent of all of this. We're just going to say the tangent of x. And then we're going to let the very inner piece, which is this x squared plus 4x plus 5, we're going to let that be another function. We'll call that h of x. And so you see, now we have three functions here, each of which we know how to differentiate. We know how to differentiate x to the 1/3 power. Derivative of tangent is secant squared, and this is just a polynomial. Then we see that the function y is actually going to be the composition of all three of those functions. Y is going to be f of g of h of x, you see. And that will be then, you see the f is the outer one. That's the cube root of x. But in place of f, I have to put the g, which is tangent, in place of the x, so it's tangent. And then it's g of h, so I have to put the h in here, which is x squared plus 4x plus 5. And there you go. So this one actually required us to use three functions to write it as the composition of three functions which we know how to differentiate. And this is what we have to be pretty good at recognizing how to do when we use the chain rule. Now here's the statement of the chain rule. It states if f of u is a differentiable function of u, and u equaling g of x is a differentiable function of x, then the composition f of g of x is a differentiable function of the variable x, and here's our rule. The derivative with respect to x of the composition of f of g of x is f prime of g of x times g prime of x. So here's our chain rule. Notice how it relates the derivative of the composition to the derivative of f and the derivative of g individually. We just have the derivative of g sitting right here, and then we evaluate the derivative of f, but then instead of putting the u back in here, we put the g of x in here. So that's our chain rule. Now, here's a different form of the chain rule down here, and this is the one we more commonly use, actually. So it states if y of u is a differentiable function of u, and u of x is a differentiable function of x, then y of u of x is a differentiable function of x, and here's the different form of the rule. dy dx equals dy du times du dx. Notice how these du's, you can think of them as canceling in a way, and you notice how this right-hand side here, you just get back dy dx, which is what we have on the left-hand side here. Now, this rule down here really is the same as this one up here, because the y is really our f in the restatement down here, and the u is the g. So dy du equals df du, and so that's f prime of u, and the u is g, so that's just f prime of g of x. So you see this right here, the dy du, that's the same as our f prime of g of x right up here. And if u is equal to g of x, then du dx, that's just dg dx, and that's g prime of x. So this part right here is just our g prime of x. And so you see it's the same rule, just stated a little differently. Now let's look at some examples. So in this example, we want to evaluate the derivative of these two functions. And here we're going to use this form of the chain rule. So we're going to use this form. And what we have to do is we have to pick u strategically over here so that we immediately know how to find dy du and then du dx. So we're going to pick u to be the inner part. That's generally what you want to do. So we're going to let this be the u, so u will be x cubed plus x squared plus 5x plus 1, in which case then the y of u will be the square root of u, and like we said, the u is going to be the... Now, following this rule, dy dx will then be the derivative of this with respect to u. Now keep in mind this is u to the 1/2. So the derivative of this with respect to u is going to be, all right, just drop the 1/2 down, subtract 1 from the exponent. So this part right here, this is your dy du. Now we have to evaluate du dx. And so we just have to differentiate this with respect to x. So then that's going to be, and so this is the du dx. So we have this piece right here matching up with our du dx. And now we just have to do a little bit of cleanup. We have to replace the u with what it is as a function of x, because our answer here should be a function of x. So everything on the right hand side should only involve x's. All we have to do is put this in place of the u, and then we'll get our answer. And a little bit of cleanup here. We'll write this piece right here as, let's first write that as 1/2 root u. Then we can put this in the numerator here and replace our u, and we get our answer. And there we go. That's dy dx. Now let's look at this one. So the same procedure here. We want to pick u to be some piece of this function so we immediately know how to evaluate dy du. And then we'll evaluate du dx. So it seems reasonable to pick the u to be the inner part again. That's generally what you're going to do, in which case y of u is going to be the cosine of u. And of course the u is our x cubed. And then dy dx. So we have to find dy du, so we have to differentiate this with respect to u. Well, derivative of cosine is negative sine. So this is going to be negative sine of u. So there is dy du times, and then du dx is going to be the derivative of this with respect to x. So that's going to be, and there we go. Now all we have to do is put what u is in terms of x in here. And there's our answer, and it's preferable to put the 3x squared plus 1 in front of the sign, just so that there's no confusion. It's not the sign of this entire thing here. It's only the sign of this piece, and then you're multiplying by that. So it's preferable to write this as. And there we go. We're finished. Now let's take a look at a little more complicated example. So here we want to take the derivative of this function. Now this function is a little more complicated because we're going to have to use the chain rule twice. Because if you notice here, we would have to write this as the composition of 3 separate functions. So that tells us we're going to have to use the chain rule twice. We're still going to use the form that should be d dx. So we're still going to use this form. Now let's pick out what we should let u be. Well, we want to let u be the inner part here, because if we let u be all of this, then y is going to be just the cube root of u, or u to the 1/3. Now notice we know how to find dy du, this piece right here, immediately then. And that's always what you need to do. You need to be able to evaluate dy du immediately. In which case then, for this we're going to get dy dx. Oh, let's also note that the u was the tangent of x squared plus 4x plus 5. So dy dx is going to be dy du. So we need to differentiate this with respect to u first. So that's going to be. And then we need to find du dx. Well, now that's a little bit of a problem, because we have to use the chain rule on this. Well, that's really not a problem. We'll just use the chain rule again. So we'll write this as So you notice I just put in place of the u, I put the tangent of x squared plus 4x plus 5, and we need to differentiate it with respect to x. Now we have to do the chain rule again on this piece, so we're going to let the inner part here be like, well, we already used the letter u, so let's use the letter v. So then all of this will equal Alright, so you notice how we let the v be the inside here. Now if we let v be the x squared plus 4x plus 5, then we immediately know how to find the derivative of tangent with respect to v. So, and also look at this right here. Notice how the dv's cancel and you get d dx of the tangent of x squared plus 4x plus 5. So that tells you that you're doing things correctly when you can cancel those and you get what you started with, the d dx part. You're doing things correctly. Now, the derivative of tangent with respect to v, that's secant squared. This piece right here is going to be 2x plus 4, and then we'll be finished. So this part is going to be secant squared of v times, and this is going to be, and then we just need to replace our u's and v's with what they were in terms of x. And finally we have our answer. So here everything is now in terms of x. So what we had to do here is we had to do the chain rule twice for this example. Now once you do enough of these problems, you can actually do these pretty quickly without having to write down all of the u substitutions like we've been doing. For example, with this problem here, the first thing we want to do is recognize that the innermost term is going to be our u. And so if we begin the differentiation process, dy dx is going to be, well, first thing we want to do is take the derivative of this with respect to the innermost term, which is the tangent term. And so we're going to get Alright, now there is the derivative of this with respect to the innermost term. Remember once again that this is u to the 1/3 power. So when we differentiate this with respect to u, we drop the 1/3 down. That's where this 1/3 came from. And then subtracting 1 from 1/3, we get negative 2/3. So here is the derivative with respect to the inner term, the tangent term. But now we need to multiply by the derivative of the tangent of x squared plus 4x plus 5. So now our u, the inner term here, is going to be x squared plus 4x plus 5. So the derivative of this with respect to x squared plus 4x plus 5 is going to be, there we go, so there is the derivative of the tangent with respect to the inner term, the x squared plus 4x plus 5, and now we need to finally multiply by the derivative of the inside term, which is x squared plus 4x plus 5. So we need to multiply by the derivative of this finally, and we get, and finally there is our full derivative of the cubed root of tangent of x squared plus 4x plus 5. So once you do enough of these, you can do them pretty quickly without having to write down all of the u substitutions, just by recognizing that you're differentiating with respect to inner terms. Now let's take a look at a few more examples that you can try. Now you can pause the video here and try to evaluate the derivative of this function. So assuming you've done that, let's go through the answer. So once again, we're going to use the form. Now I'm going to do this sort of quickly to show you that you don't have to write out everything in as great a detail as we did in the previous examples. So for this one, we're going to let the u be the inner part so that we know how to immediately evaluate dy du, because then y is going to be u to the 10th. And we know how to evaluate dy du right away. So dy dx is going to be the derivative of this with respect to the inside, which is u, so that will be 10. Okay, so here is dy du times du dx. And there is your answer. Just note that this part right here is our dy du, and this part right here is the du dx. And that's all you have to do. Let's take a look at another example. Now why don't you pause the video and try to evaluate the derivative of this function. Assuming you've done that, let's go over the answer. Now let's notice that you can write this as, this is really the sine of x cubed. Right, that's really what the sine cubed of x means. It's really the sine of x, the whole thing cubed. So we're going to pick this part right in here to be our u, because then this is u cubed. And we immediately then know how to evaluate dy du. So dy dx, we'll write that as dy du, du dx. So the derivative of this with respect to u, then u is sine, so the du dx becomes cosine of x. And then we just replace our u. And we have our answer. Let's try one more. So why don't you try to evaluate the derivative of this function? Now for this one, you're going to have to apply the chain rule 2 times. So assuming you've tried it already, let's go through the answer. Now notice that because it's the tangent squared, that you should really think of this as it's really like that. Alright, so what should we pick our u to be first? Well, let's pick it to be the inner part right here. Everything here, all the way over to here. So then this is just u squared. So then we immediately know how to evaluate dy du. It's just going to be 2u. So dy du is going to be just 2u. Now du dx, well, we're going to have to, let's write that like this. Let's write that as d dx of the tangent. You see, now we're going to have to use the chain rule again on this part right here. We're going to have to do the chain rule again to evaluate the derivative of this. So, think of this in here as being a v, and so this is going to be 2u times the derivative of tangent. I'll write it out like this, d dv of the tangent of v times dv dx. Notice how the dv's cancel, so you're getting d dx of tangent of v. That tells you you're doing things correctly. And so this is 2u times this part right here is the secant squared of v. And for v, I'll just put right back in place the x squared plus 5x plus 1. And then v is the x squared plus 5x plus 1, but I have to take the derivative of that, so that's going to be 2x plus 5. And then you just have to put the u in. The u was, all of this up here. This was the u. All of the tangent of x squared plus 5x plus 1, and we get our answer. And there you go. We have our answer. Now let's take a look at the proof of the chain rule. Now we're going to prove the chain rule, and we're going to prove this form of the chain rule involving the f's and the g's instead of the dy dx equals dy du times du dx. We're going to work with this form. Now before we start our proof, let's recall the two forms of the limit definition for the derivative that we have. We have this one, limit as delta x approaches 0, f of x plus delta x minus f of x over delta x. This is the one we most commonly use. And we also have this form, limit as h approaches x, f of h minus f of x over h minus x equals f prime of x. And we can get this form, remember, just by letting h equal the x plus delta x. And then delta x becomes h minus x. So if we replace this with an h minus x as we have down here. Now also notice that as delta x approaches 0, that means the h is getting closer and closer to x. So we replace this with h approaches x. So it's the same thing, just written in a little different form. Now let's start our proof. So we start out with d dx, f of g of x, and we are going to go back to our first limit definition here. Alright, so that's just our limit definition here. In place of the f here we have f of g. And now we're going to do one of those little math tricks again. We're going to multiply in and divide back out by the same thing. So we're going to rewrite this as So you see, all we did is we multiplied in by g of x plus delta x minus g of x, and we divided back out by the exact same thing. So these two terms here actually would cancel, and we would recover this. Now let's notice this. As delta x is approaching 0, this part right here, well, this just looks like the limit definition for the derivative of g, and that's exactly what it is. So as delta x goes to 0, this part right here is approaching g prime of x. Now let's consider this part right here. Well, notice as delta x approaches 0, g of x plus delta x, that's getting closer to g of x, right? So let's just note that up here. As delta x approaches 0, g of, that's approaching g of x. And that's because g is going to be a continuous function. Why is g a continuous function? Because we assumed its derivative exists. So it's continuous. So you see, this piece right here is sort of behaving like the h. It is. That's exactly what it is. It's the h over here in this limit definition for our derivative. And this piece right here is like the x over here. It's that piece right there. That's like the x. And so this g of x plus delta x minus g of x, that's the h minus x. G of x right here is like the x sitting right here in the parenthesis of the function f up here. And so we see that this part right here exactly matches with this. If we think of the g of x plus delta x as being our h, and the x as being the g of x. And so this piece right here is approaching f prime of g of x. And so these two are being multiplied from this multiplication right here, and we get our answer. And that's exactly what we wanted. And so that is the proof of the chain rule. Now there's only one little problem with this proof. You notice how we're dividing by the g of x plus delta x minus g of x. Well, what if this were 0? What if this happened to be 0 near the point x? Well, that is a little problem, but it can be fixed. But we're not going to do that in this course. That would be saved for a more advanced math course like advanced calculus or an analysis course. So this proof is pretty good. It just ignores that one little point. What if your denominator happens to be 0 at some locations as the delta x approaches 0? But that's okay. All right, so that concludes our discussion of the chain rule.